Thank you very much to the organisers. As I said earlier, please, those of you who know more Italian than I do, don't be too offended by my poor Italian. It's been very tough to practice now that we're in lockdown, but I very much appreciate the fact that the organisers have organised the conference at this time. It's very good to see people, of course, much better to see people in person, but Italy's had a very tough time, and it's been a great pleasure to be invited to this conference. Thank you very much to the organisers, and to see some of my dear friends again and to meet some new friends. So I wanted to talk in a kind of old-fashioned Plato's Academy style today. Normally I give all my talks on the blackboard, and as I was saying to some people earlier, it's very difficult for me. I have to sort of hold equations up to the page and it's terrible. So I thought rather than that, it's the last talk of the day for me. It's the last time before I need to have dinner with my family, and it's the first talk on day 2 for you. So I didn't want the talk to be too technical, nor did I want there to be too many equations passing between our screens. So in the abstracts on the conference website, I put a link to the archive article about which I'll be speaking. So if you wanted to look up that, that's fine. I'll be drawing references to there, but very loose references. That's just all the stuff's written down there if you want the technical details. Like a kind of old-fashioned talk, if you want the details, you can see those in that paper, but I'm just going to try to talk a little bit about the history of the problem that I've been working on recently. So everything I say in this talk happens to be joint work with my very good friend Mike Mossinghoff at Center of Communications Research in Princeton in the US, and one of my PhD students, Valeria Staryczkova, who is about 1.5 years through her 3.5-year PhD. So the problem we have to look at is a very old problem in number theory. But before I tell you what the problem is, I want to creep up to it. Rather than just launch in and say, I want to bound this, and I want to bound this, and I want to do something with Siegel zeros, let's just take it nice and easy. So one of the first proofs that I saw that caught my attention when I was a graduate student in England was the proof of the prime number theorem via the old-fashioned approach, where one would use the non-vanishing of the zeta function on the line sigma equals 1. Now, there's many proofs of the prime number theorem. Of course, there's a so-called elementary proof of the prime number theorem. But what took my fancy in this, and you find it, you know, it's all in the standard textbooks, Titchmarsh, Monty and Vaughan. I should say Montgomery and Vaughan, but I have a son called Monty, so I assume Hugh Montgomery doesn't mind if I call him Monty. I'm going to call him Monty. So you find it in Monty and Vaughan, you find it in Titchmarsh and Davenport and all the standard texts. So the two original proofs of the prime number theorem in 1896 both made use of what, to me, as a graduate student, a fresh-faced, I didn't have a beard back then, as a fresh-faced Australian going to England for the first time, what was strange to me was that they both seemed to use a rather mysterious trigonometric polynomial, a polynomial that looked to me as if it came from nowhere. And often in these books, there's a little cryptic remark given underneath, like any other equivalent polynomial will do, or you could use something else and it'll work just as fine. So let's talk through where this polynomial comes from. Well, if I had to give a 3-sentence proof for how you prove the prime number theorem, well, first you do some stuff and you hope that that stuff means that if you show there are no zeros on the line, real part of S is 1, then you can deduce the prime number theorem. In fact, those two statements are equivalent, but let's go about it this way. So how do you show the non-vanishing of the zeta function on the 1 line? That's the question. Well, all you need to know about this is that the zeta function is almost entire. It's analytic everywhere except that S equals 1. And all you really need to know is that it has a pole at S equals 1. You don't even need to know it has a simple pole, just a pole is enough. So what you do is this. You look at the point S equals 1, where there's a pole. You look at the point S equals 1 plus IT, pick your favorite non-zero t, like, I don't know, 20 or something. So your S equals 1 plus IT. Then you look at another point, S equals 1 plus 2 IT. And then you know that at S equals 1, there's a pole. You assume at S equals 1 plus IT, there's a 0. And then you play some game where you use some trigonometric polynomial. I haven't told you what it is yet, but you play some game and then you deduce from that that zeta of 1 plus 2it has a pole, and you know that that's a contradiction. So you need the pole at 1, you assume the 0 at 1 plus it, you play this trigonometric polynomial game, and you conclude there's a pole, hence contradiction. So you have this non-negative trigonometric polynomial. Now, when you look at it, it looks like something like 1 plus 2 cos theta plus cos squared theta. That's what it looks like. And you say, okay, well, I guess that's non-negative. So when you look at this polynomial, that somehow relates these things. Why? Because it relates values of theta to values of 2 theta. So it relates exactly what you want. It relates 1 plus it to 1 plus 2 it. Okay. So in all these books, there'll always be the remark, any equivalent polynomial will do. We just chose this one, or Della Valle-Poussin just chose this one, or Hadamard just chose this one. And what struck me as strange was that in some books, they would say, any polynomial will do. In other books, they might say, any similar polynomial will do. In other books, they may say, any polynomial having these characteristics will do. That's the most precise statement. You can't just take any polynomial. And for the history of these polynomials, who better to consult than a young man called Tim Trudgian, yes, who wrote an excellent article years ago, zero-free region for the Riemann zeta function. And what we tried to do in that paper was to trace the development of this trigonometric polynomial that goes right the way back to the proof of the prime number theorem, and was investigated thoroughly by Landau and others. So here's one aspect of the talk where, if you're not interested in the rest of what I say, one could approach the following problem without any number theory. So in this paper I wrote with Mike Mossinghoff, and it will be referenced to from the paper I put in the abstract, this problem of finding the best polynomial is still open and very difficult in my mind. It uses zero number theory and just uses harmonic analysis. So if one was interested in a problem to give to someone who was interested in playing some Fourier kernel games and other things, there is zero number theory in looking at so-called Landau's problem on this trigonometric polynomial. So that's a side thing that one could get into. But what struck me about this was that you couldn't just use any old trigonometric polynomial. It had to satisfy certain conditions. Now, if all you want to do is prove that there is a zero-free region, then all of those textbooks are correct. Any polynomial will do. This one or that one, it doesn't matter. If, though, what you want is to find a very wide zero-free region because it's useful for some application, someone wants to do something with the prime number theorem, someone wants to do some computation, someone actually cares about the width of the zero-free region, then instead of just getting out some constant in the zero-free region, you could figure out what that constant is. And that constant's useful if you want to play games like measuring how big the nth prime number is, or measuring the error term in the number of zeros of the zeta function to a certain height. All sorts of places does it pop up. So if what you wanted was a so-called explicit result, where you wanted to find out the size of the zero-free region, not just the shape, but the size, then the choice of polynomial very much matters. So then the question becomes, if what we want is the widest zero-free region we can come up with, then we should choose the best trigonometric polynomial, whatever that means. So if what we want to do is have a very good zero-free region, because we want to use that for prime number theorem, I mean, in my very layman's attitude, the idea is I only care about the zeta function because I want to count primes in a clever way. If someone figures out a way of counting primes in a clever way, then we just put the zeta function in the bin. I just haven't met anyone in the universe who knows how to do primes without the zeta function. So if we want to estimate primes cleverly, we need the zeta function. We need the properties of the zeta function. The more you can squeeze out of the zeta function, the better for everyone. So the wider you can make the zero-free region, the better. Of course, the widest you can make the zero-free region would be if you had the Riemann hypothesis. And unfortunately, we don't have enough time to prove the Riemann hypothesis in this talk. Oh, I should have had an hour slot. Terrible, terrible, terrible organizing, terrible. So instead of being able to prove the Riemann hypothesis, what one wants to do is, I don't know what the idiom is in Italian, but in English, it's to be content with the crumbs from the table. You don't want the loaf of bread on the table, but the crumbs are okay. You'd love the Riemann hypothesis to be true. But if you can't get that, then a wide zero-free region is still okay. So we want the widest zero-free region. So we want the best trigonometric polynomial. And keeping to my kind of Plato's Academy style of talking with my hands, I'm not even going to write down what the trigonometric polynomial is. I don't even have a pen. How can I write anything down? What a terrible speaker. So instead, what I wanted to do was to say, if we're interested in this trigonometric polynomial, then we look for the best one or an almost good one. And then we get an excellent zero-free region for the Riemann zeta function. So that's the creeping up to this problem that I wanted to do in the first 10 minutes or so. This connection between the prime number theorem, the zero-free region for the zeta function, and this mysterious polynomial. So mysterious, I haven't even told you what it is. So now, what about the paper I was talking about? Well, the paper I wrote with Valeria and with Mike was looking at a similar problem, but with Dirichlet L functions. Now, there are many ways that you can generalize the Riemann zeta function when you move to more exotic L functions. One philosophy or one idea that one has is that the zeta function on the one line, so zeta of 1 plus it, behaves very similarly to a Dirichlet L function L of 1 chi, where chi is a Dirichlet character mod q. Now, there are reasons of why it behaves similarly. We don't have to worry about those now. But we think that almost anything you can say about zeta on the one line, you ought to be able to say about a Dirichlet L function L of 1 chi. So in particular, if you can show the prime number theorem that zeta of 1 plus it is never 0, then you expect to show that L of 1 chi is never 0. And that's true. That's Dirichlet's proof of the prime number theorem for arithmetic progressions. So now, again, if we creep up to the problem that I discussed in the paper, what's the point of looking at the zeta function? There are no zeros on the line sigma equals 1. And if we work a little bit harder, we can push that zero-free region inside to sigma less than 1, to the real part of S less than 1. So we can make a small saving there. We can say not only are there no zeros on 1, but no zeros too close to 1. That's great. So one expects one should be able to do the same thing for a Dirichlet L function. And almost all the time you can. You can show that L of 1 chi can't have, that L of S chi rather, can't have too many zeros close to S equals 1. And of course, if you know what I'm about to say, then you know what I'm about to say. What an excellent logician I am. If you know what I'm about to say, then you know what I'm about to say. The problem, of course, comes in terms of the so-called Siegel zeros or exceptional zeros. What happens if you have not just some random character chi, but you have chi, which is a real character or a quadratic character? You may have a 0 on the real axis inside the critical strip, which can't occur for the zeta function. I can give you a 3-line proof of why that can't occur. But for a Dirichlet L function, you could have a real 0, a 0 on the real axis inside the strip. And it could be really close to S equals 1. The closer it is to S equals 1, the more you're in debt, the more it will bankrupt you. So you don't want one of these exceptional zeros too close to S equals 1. So hence the title of the talk, non-zero and then some. You want to show, you know for a fact, I'll give it to you for free, that L of 1 chi is not 0. So by continuity, Dirichlet L functions are continuous. Okay, non-principal one's fine. So Dirichlet L functions are continuous. If L of 1 chi is non-zero, then if I take an S very, 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 very close to 1, then L of that S chi, that's also non-zero. The question is, how far can I push it away from S equals 1 and still show that it's non-zero? I want to show it's non-zero. I know it's non-zero at S equals 1. And then I want to say, not only is it non-zero, but I can bound it away from 0. So what I want is a lower bound on a Dirichlet L function. That's what I want. I want a lower bound on L of 1 chi, or a lower bound of L of S chi, where S is very close to 1. That's what I want. S on the real axis, very close to 1, just a little bit inside, and I want a lower bound. The better the lower bound, the better for everyone, because then the better error term in the prime number theorem for arithmetic progressions. So going back to the first 10 minutes of the talk, when I said we only care about the Riemann zeta function because it tells us stuff about primes, one could make the same claim. We only care about the Dirichlet L functions because they tell us something about primes and arithmetic progressions. To get the best error term for primes and arithmetic progressions, you want zeros nowhere near the line S equals 1. In particular, you want to push those potential Siegel zeros as far away from S equals 1 as possible. Okay, so it's very tough to make progress with Siegel zeros. So of course, being a man who doesn't want to do any tough work, we didn't look at Siegel zeros. Why do hard work when you could do easy work? So instead, we want to say for other Dirichlet functions, not the quadratic characters. That's too hard. I mean, I guess if I did that, then I can invite myself to St. Petersburg for a field. I'm still under 40, even with the gray in my beard. I'm still under 40. So I go to St. Petersburg next year for the Fields Medal. Yes. So rather than tackle Siegel zeros, I'll tackle the easier problem. So can I show that for Dirichlet functions, not with a quadratic character, but for some other character, I still have L of 1 chi bounded away from 0. And just like the zeta function, if I wanted to show bounded away in some region, I can do it, and it's a standard proof, and any trigonometric polynomial will work, just like the zeta function. But if what I want to do is to say it's bounded a lot away from 0, and I want to tell you how big it is bounded away from 0, give you a number that you can use for some calculations you want to do on the side, then I need to choose the best trigonometric polynomial. So this idea of connecting the prime number theorem with the Riemann zeta function and saying whatever we think happens on zeta of 1 plus it should be similar to L of 1 chi. This is an idea that's been explored many times. And my dear friend and collaborator, Alex Zanguasco, who's going to talk after me, he and I wrote an article together where we looked at the size of Dirichlet functions, L of 1 chi, under the generalized Riemann hypothesis. There's many things one can do with looking at these analogies between the zeta function and Dirichlet functions. So that was a nice, I know Professor Languasco's not talking about that, but it was a nice free advertisement for our talk. And I'm here talking for 10 more minutes, so even more free advertisements, yes. So what we're gonna do with Dirichlet functions, the idea that Mike and I had, and I always have ideas, the idea was, well, everyone seems to be using fairly weak polynomials, fairly weak non-negative trigonometric polynomials for their Dirichlet function case. Why don't we use the very, very good one that we found in our Riemann zeta function paper? Why not? We spent all that time, we spent all that money. I had to drink all that whiskey to drown my sorrows about all the errors I made in the paper. So why not get something out of that and take exactly what we did in the zero-free region for the zeta function case and just put that straight in to the Dirichlet function case and write a 2-page paper and we're done. And I thought, seems too good to be true, because if you could do that, someone would have done it. If I'm clever enough to figure it out, someone else is clever enough to do it. So I thought, oh, we'll give it a go nevertheless. So we tried this, and then I realized there were technical obstructions. There was a reason why people didn't just take these better trigonometric polynomials and put them in. Lots more things to test, and I won't tell you what they are. So they were too tough for me to test. I couldn't figure out a way around it. So I said, those who can't teach. So I thought, why, if it's too tough for me, I have students who are very, very clever. If it's too tough for me, Valeria Starichkova is very clever. Well, she'll figure it out. And sure enough, she did. So she figured out a way of moving around these technical obstructions. So now, and only now, do we have the ability to say any good trigonometric polynomial you have that works with the zeta function will also work for these Dirichlet function cases. And that's great, because that means, I talked about it about 12 minutes ago or so, if someone gives this problem to a colleague in harmonic analysis and looks at the Landau problem for the best trigonometric polynomial, which is still open, it's not even clear to me that there is a best trigonometric polynomial. Like maybe there is, I don't know. But if someone's able to improve on the polynomials in that classical setting, then thanks to the technical circumventions that Valeria was able to do in our paper, we're able to lift that work directly into the case for Dirichlet functions. So there are some other small points about it, which is Mike did awful lot of computation based on how to find good polynomials, because there's some lower order terms. It's very difficult to control. So Valeria got around the technical obstructions. Mike found excellent trigonometric polynomials that we could use. And I sent encouraging emails to everyone. And hence I was a co-author. Yes, that's the best way to be a co-author. Just send encouraging emails. I believe in you. You can do this. Yes. So one question that one might ask, I know it's difficult to ask questions on Zoom. I mean, I've always found it difficult to, I mean, if you try to, I don't even know how to put my hand up in Zoom. I just kind of do this, terrible. So it's difficult to ask questions. So let me do you the honor of asking a question for you, or thinking of a question for you. Maybe we get to it, maybe we don't. But one thing one might think of is, okay, how many more papers are we going to see from Tim Trudgian and friends on this trigonometric polynomial? Well, probably not many, in that I've run out of ideas. What I'd like for someone to do, though, is to say, whenever a colleague is looking at a zero-free region for something much cleverer than I can understand, like a Rankin-Selberg L function, I don't even know what that is, right? If someone's doing very exciting things, then sometimes, not all the time, but there are some examples. You can find them on the archive. Do I have them here? Maybe I don't. I'm happy to email them to people. Oh, right. A paper by Humphreys and Thorner, a paper by Hoey, Iskander, Jew, and Suarez. Just two papers I found in 2021 on the archive that gave zero-free regions for what I would call, in my very low-brow mathematical perspective, as exotic L functions. In my mind, if it's not the Riemann zeta function or the Dirichlet L function, it's not that I'm not interested in it. I just don't understand what's happening. So if people for different applications are looking to find a zero-free region and they want it to be really wide because they have some application to Sato, Tate, whatever, I have no idea. If they're wanting to do something that's very exciting, then they're going to want to have the best tools at their disposal. They're going to want to know, don't just do the same trigonometric polynomial that's been done for the last 120 years. That will work fine if you want any old region out. But if you want a good region out, or the best region out, then you should try to use a better one. So part of the reason I'm giving the talk, not just to advertise the work that we've been doing, but was to try to say, I'd be very keen, I don't have any ideas, but I'd be very keen if someone was to look at this idea of the trigonometric polynomial in the Landau sense, which has nothing to do with the zeta function, nothing even to do with number theory. It's just a bunch of cosines, 1 plus something times cos theta, plus something else times cos 2 theta, plus something else. And you want to use cancellation. You want to use interaction between the coefficients to force the polynomial to be positive. You can't cheat and take, say, 1 plus 1 over a million times cos theta plus 1 over 2 million times cos 2 theta and have all these terms be too small. You have to use genuine interactions between the coefficients to show that the polynomial is non-negative. And that comes back to the fact that you need, way back at the start of the talk, I said the 3-card trick that we're playing here, when we do, it's the same for Dirichlet L functions, but when we do for the Riemann zeta function, there's a pole at s equals 1. We assume there's a 0 at 1 plus it, and then we hope to show there's a contradiction at 1 plus 2 it. And we have to have these polynomials, if you like, this corresponds to the constant term in the polynomial, this corresponds to cos theta, and this corresponds to cos 2 theta. We have to use the fact that to obtain a contradiction, that there's a pole up here, we have to, if you like, have this pole overtake that 0. So we can't just use any old polynomial in order to obtain the contradiction. So another question one could ask is, well, we prove something, and you can see it in the archive paper if you like. We prove something. We improve, not by much, we improve a little bit on what was known, done by Stéphane Louboutin for Dirichlet L functions. We improve on the lower bound. Now, a question I would always ask if I was a chair is, well, if you improve it by a little bit, could you work harder and improve it by a little bit more? That looks very difficult to do. It looks difficult to do because, and if we go back to the Landau problem, we don't know what the best trigonometric polynomial is, but we know it has to lie in a very small range. Whatever properties it have, those properties are very narrowly limited. I'm speaking deliberately vaguely now. We know that whatever the good one is, it has to be in this very narrow interval. So improving it by much is not going to improve on these other results by much. But it would be nice to know that there is a limiting value, that there is a way of finding the best trigonometric polynomial. So it looks difficult to improve on it by much. But hopefully, it improves on the result, which is a win. And if any editor or referee who happens to be looking at the paper is listening, it is an excellently written paper. And of course, I would say that. So if what you wish to do is to improve on it further, you would need a new idea, which I would welcome. But it was a lot of fun working on it. It was a lot of fun to explore in my mind this connection, which also I explored with Professor Languasco when we looked at this paper of L functions versus Riemann zeta function on the one line. It was quite fun to explore that. I don't want to use duality because it has a mathematical meaning, but it was quite fun to explore the interaction between those two sides and to see what needed to be done in order to lift these results from the Riemann zeta function case over to the Dirichlet L function case. Thank you very much for your kind attention. It's been a joy to be here at the meeting. As I said at the start, to our Italian colleagues, of course, it'd been nice to see you in person at some point, or to host you out here to Australia at some point. But it really was a treat, and I'm very grateful for being invited to this meeting. Thank you very much.